thanks for giving us the opportunity to talk about something that we've been passionately working on over the last month, which is Teapot, which solves some of our problems that we had while we were deploying honeypots. Teapot is a multi-honeypot platform that we use internally nowadays that makes the deployment fairly easy, has near to zero maintenance efforts, and solves a lot of problems that we had during the setup of our honeypot network. So first of all, we will split the talk in two parts. I will take the first part, which is talking about what we've established at Deutsche Telekom as part of our early warning system and our honeypot network. And Marco will then go more into the details of Teapot and the architecture and how it's technically done. So just a short introduction. We are both from Group Security Services at Deutsche Telekom, which is the central internal IT security provider. I've been joining Deutsche Telekom in 2010. I previously worked for the government as a incident handler for the national or the governmental CERT. We're both, safe to say, gadget guys. We love playing with new technologies and gadgets. So beside the interest for security, we also like playing around with new technologies, and that's how we finally ended up with Teapot.
Yeah, my name is Marco Ochse. I joined the Deutsche Telekom in the year of 2010. And in 2011, I joined the group security, and I'm responsible for enterprise mobility management and office security, and have a lot of projects there. And I joined the Honeypot group at Deutsche Telekom shortly after I joined the group information security in 2011, and since then we're working on Honeypot projects. And yeah, well, before that I was working 10 years in the finance sector, and yeah, I'm a gadget guy, so I'm addicted to gadgets, technology, and of course security. And yeah, I'm proud to be here.
Okay, so just a couple of words to the about the early warning group that we formed at Deutsche Telekom. We started in 2010. We developed we deployed the first web honeypots back then, and it's a very small group of honeypot enthusiasts, people that are into security, that are willing to try new things, understand attacks that are happening on the internet. And mind that all what we do here is done next to our day job, so it's not a full-time employment that we have here, it's just some spare time that we can dedicate to this project. We don't have anything like a commercial project. This is or a product. This is something that we do because we like it, because we think that it's important. And although it's not a commercial product, we really get very high attention from the top management. We have our board of directors. Everyone knows what the Honeypot group is inside of DT and what we do, and they really appreciate it. So it's a fun thing to do. So first of all, I want to talk about how we set up our honeypot network at Deutsche Telekom and what our experiences with setting up such a network were, which we wanted to solve. So right now we have around about 180 sensors, which consist of honeypots and application level firewalls, and we place them in several access networks, like in data centers, in our own data centers, in data centers of partners. We have them running in DSL customer premises. We have them running on the mobile IP network where the smartphones usually get their IP addresses from. So as a telco, it's fairly great for us to cover all access networks that we could find. Our sensors that we deployed are mostly based on open source software. A lot of software that comes from the HoneyNet project that we're using, that we're very grateful for using. Like Honeytrap, Dionea, Kippo, and stuff like that, software that you probably know very well. We also did some own developments like NodePod and MySQLPod, which Marcus developed, who's taking pictures over there. And so we try to enrich the landscape of sensors that we could deploy. The idea was that we try to cover all the protocols that we internally use as service providers, so that we could see if they were specially attacked on. The honeypot software that we use is mostly simulating known vulnerabilities, but we also have some self-running components there. And after deploying the sensors, they all feed back to a central analysis system, which we call the early warning system. And that's basically our backend that we created, that we developed. It takes the data from the Honeypot sensors, which we think is the important data totally from a telco point of view. So we're not into malware analysis or stuff like that. We're mostly interested on the IP data. We've connected a lot of partners, international partners, other telcos. We have partners in the academia. We have partners in the public sector, which we all connected to our backend, and they all feed data. And we focused on, as we're a very small team, we focused on the complete independent and automated processing of those attacks. So everything we do here, we don't have the manpower to do manual analysis and stuff like that, so everything has to be automated. Finally, we can create statistics. We have some search capabilities. We can do some analysis, which we do on demand, but the main goal is to create alarms and notifications for us, for our abuse department, for our partners. So in case, for example, a Dodgy Telecom IP address gets caught in one of those sensors as an attacker IP, there will be a completely automated process that will be triggered, and that is informing the abuse department, which will then inform the customer that he has a problem with his computer that is probably infected with some malware and is being used for attacks. So that's just a brief overview of the system. And now we'll talk about a bit about the Honeypot deployment that we have and the challenges we had during the deployment. So when we first started in 2010, our first honeypots were installed on pure hardware. So as you probably know, most of the honeypots have a very low footprint, so you don't need a lot of processing power. So this is something that is overdone, too much processing power for a honeypot. So we started then to go into virtualization. We virtualized the honeypots. This is an example of a smartphone honeypot that we developed in 2011. Which is on the mobile access network and is trying to simulate mobile smartphones like Android and iOS, which can be attacked. And we finally found some specific targeted attacks against the network stack of Android and iOS. So this is something that we did in a virtualized environment. We put them on the real cellular network. We couldn't just hang them into the backbone, and which is for the mobile IP space, but we still had to put them online in the way that all other smartphones got online with a wireless stick. And after going into virtualization, we thought, well, what else can we do? And as I mentioned before, we are kind of playing around with new toys, and the Raspberry Pi emerged in 2012, so we bought some of those and thought, oh, this would be a nice thing to put some honeypots on that, because they're really low cost. And we compiled the software that we used for the Raspberry Pi. As it's an ARM architecture, we had to recompile that and kept it running on this system. And we got a lot of, as I said before, a lot of management attention, and the manager said, oh, we want this in all our national companies. So Dodgy Telecom has a lot of subsidiaries in other countries like Netherlands, Croatia, Greek. So we had from the very top management, we had someone say, okay, you send out those honeypots into those national companies, and we could send them each a couple of sensors, and they deployed them in the network. And this was great for us because we could broaden our honeypot sensor base very easy and very quickly. But we, which I will talk about later, had a lot of issues with that, because it's not that easy to maintain that many systems and still keep a stable state. So what else we did was we did some proof of concepts, like installing honeypots on Android devices, on-device honeypots. And we built some things. As the managers always ask for something, oh, honeypot is a cool concept, but could you just give me something that I can present? And we developed a honeypot based on a Raspberry Pi with a wireless interface and a touch screen, so you could just show, oh, look at this, these many attacks have been happening since then, and it's got some nice fancy statistics. And well, that's some of the parts we did. And this finally led, all the experiences that we made here finally paid into the concept that Marco will talk about later, the teapot concept, because we made a lot of experiences here. And This is one thing that we have as a low-hanging fruit from all the data that we gathered. We, as we said before, our purpose is to identify infected customers. So we are mostly into the IP address data. So this was something that we did in 2012, which back then also used a component of that was by the HoneyNet project, which was HoneyMap, to just show the IP attack data that we had on a public website. We got a lot of attention back then, and we always continued to develop that. But that's something that is a very C-level management tool to just raise awareness. And as I said, it was a low-hanging fruit for us to visualize the data that we have and make it accessible. So this map updates in real time what is happening from where a sensor in another country is being currently attacked. So just a couple of words for the challenges and experiences we've made. So first of all, we've worked with a lot of different hardware platforms. We had from full hardware virtualization to low-cost hardware, but we also had to do a lot of tailoring to those platforms, and especially when it's about performance, we have the Raspberry Pi, which is performant enough if you have a certain honeypot daemons running, but if you go and switch the honeypot daemon, it will be not powerful enough. Second is the architecture support. We had to recompile every software that was running on our x86 hardware we previously used back to the ARM architecture, so that was a bit of a difficult to do and time-consuming. Then another thing we should consider was the data center security policies. Once you put a honeypot, for instance, in a data center, you always have to make sure that you meet their security policies, like outgoing traffic. You have to somewhat meet their security standard that outgoing traffic, for instance, is not allowed, and you have to deal with that. So that's kind of difficult, as well as the network segregation to keep it even in an unstable state, to keep it separated from the other productional systems that are there. Another thing we had was that we had a limited number of honeypots per device. That was because some of the honeypot daemons did not successfully run in parallel, so you could only have either type of honeypot daemon running. So we tried to solve that problem as well. The second part is the deployment. When we were asked very frequently, could you help us install a honeypot? Because it's a very cool concept, and we have all the other stuff, but we want to have a honeypot as well. And we said, yeah, of course, but it's always a manual process. We always had to either go on premise and install it, or we had to remotely install it. So that was always time-consuming. And there was no solution that fits all, because we tried that with the Raspberry Pis. We did a pre-configured image that has a bootstrapping mechanism that we could just send out, and it would configure that during first setup. We tried that. It worked partially, but not very reliably. So most of the time, the solutions had to be tailored to the customer. Then we also used configuration management tools in order to be able to access all the nodes, to push updates to all the nodes, and have also made some very mixed experience with that. Another issue is thing to consider is maintenance. As I said before, we were able to access the systems, which was a lifesaver in most of the time. So, but that was mostly debugging was mostly a manual process. You had to go on the system, see what's happening. We had some where, for instance, inodes the system was running out of inodes, and it was exactly the same system as another one, but the other one hasn't been attacked in that way. This system has been attacked. So debugging was always manual process and very time-consuming. And unfortunately, we lost some systems which we installed, and we weren't unable to relive them, so we had to redeploy them. And finally, data aggregation, and we heard a lot of that in the other talks before, data visualization and stuff like that. If you have such a central component where all the honeypot data comes in, you have to define what kind of data you want to see, how you want to process your data, and what you really want to do with the data. That is very crucial. So this was just a very quick wrap-up of the experiences that we've made during the establishment of our honeypot network at Dodgy Telecom. And I'm going to forward to Marco, and he will explain you how we solved most of those problems with our new architecture and the new Honeypot platform. Thanks.
So with the challenges and experiences we had to rethink a lot of things, and we were setting for new goals and some innovations in that matter. And for hardware, that's where it comes in, the fact that we had so many platforms to support in the past, so that we wanted to have a solution that fits all our architectures, as long as it runs Ubuntu and as long as it is a 64-bit processor below it, mainly Intel and AMD, of course. Of course, we had virtual environments for development for some people who work at home or want to have a honeypot at home. And then virtual box or VMware comes in, even if you have an ESX farm, of course. We wanted to support that. What also is very popular is the Amazon EC2 cloud, and of course the Google Cloud platform they wanted to support, so that you can upload an image there and or use an image there and have your Honeypot installation run there. As André already told you, we are a small team, and that's why we need an installation process that is which is completely automatic or semi-automatic, and involves zero to no interference from the administration side, so that we can have the installation done in 15 to 30 minutes, for example, without any administration interaction. Each Honeypot installation that we wanted to have should be an exact replica of what we had in mind with our master system, so that every installation feels completely the same. And since we're using all the open source tools from the HoneyNet project, GitHub, or Linux, we want to give all that back to the community as an open source solution that anybody can download, try, contribute to, and use it. And one of the major drawbacks that we had with the Raspberry Pis was we could only use one honeypot at the same time, or two honeypots at the same time. And with a new approach, we wanted to support at least 2, 3, 4, or a number of honeypots or applications on one machine, on one installation, so that we're not limited to one honeypot at one time. Yeah, with maintenance, it's the same problem as with the installation or deployment. Small team, and we wanted to have automatic updates. So with zero to only low maintenance on the client. So everything should be automated, self-sustained. If a process crashes or something like that, or an application crashes, it should revive itself, and so that everybody can use the solution even without any technological background, how to debug it. So for an internal solution, external access to the honeypots were crucial for the configuration management, for debugging purposes, and with a community-driven solution, of course, external access should be optional. So you want to set your own password, or of course your own access to the system, and not have anyone else have access to it. For the data aggregation part, we wanted to support at least 3 flavors. So the first one, as André already showed you guys, the security dashboard from the Dodgy Telecom, where you submit data to. Then a community dashboard where the community honeypots deliver their information to, or the events to, so that which is publicly available as well. And something that is really new for us when it comes to honeypots, a local dashboard based on an Elasticsearch, Cabana, and Logstash stack, so that you can view your local events even if you opt out using HP feeds or our Telecom backend solution. So Teapot is now a multi-Honeypot platform. It uses Ubuntu as a base system in the 14.04.2 version, but heavily runs on Docker. So everything we do when it comes to the honeypots or any application that is installed is actually a Docker image and a Docker container running on the client. And this is actually really cool. Docker is the one and only technology which made this platform possible as a base. And what we do is actually, I'll go into more detail later, is we have our log aggregator here that sends back logs back to the Deutsche Telekom backend, the Sicherheitstacho. Then we have 4 honeypots running and Suricata, which is a network security monitoring system, which sends log information to the ELK stick so that you can view it locally with the Cabana Dashboard, and this is really beautiful. We use Docker Hub as a central deployment platform, so all the images which we create from Docker files will be deployed to Docker Hub, and during the installation process, these images will be downloaded onto the client. So whenever you install a Teapot, you always have the latest installation, the latest information, the latest code onto the machine. And the whole installation only takes about 15 to 30 minutes to finish, depending on the line speed that you have for your internet connection. And of course, this is really cool because it's the first time that we can use an external deployment platform like Docker Hub to install a machine and have the possibility to always have the latest image. So this is a picture of the Cabana Dashboard that we use locally. It's very beautiful and enables even people who run the solution at home and who don't want to use the backends like HP Feeds or our Telecom background solution, the security dashboard, to locally view the events at home, at an enterprise who wants to opt out, or somewhere else. And this is really cool. Currently, this is in beta stage, and we can only view the network security monitoring alerts there from the Suricata. And we plan to introduce the log events from all the honeypots that we run on Teapot. So this should be available within the next version. With the beginning of last week, also support the Amazon AWS cloud with EC2 images. So when you install an Ubuntu image in a 64-bit flavor, you will be able to check out a GitHub script that converts the Ubuntu installation into a Teapot installation, and this takes about 15 minutes. Yeah, we also were looking for a hardware platform. Since we were using the Raspberry Pis, we still wanted to use and support a hardware platform that you can run at home, and which is supported. And we were looking for a while, and we came across the Intel NUC platform. There are 2 things that are really cool about it. It's a small form factor, and it's powerful enough to drive our solution without any problems. So this looks rather complicated, right? So, but the matter of the installation is 3 steps. Get the image, fire it up, and follow the installation process, which is completely automatic, except you have to enter the keyboard layout, and you have to enter the time zone. That's all. And everything else is completely automatic. It installs automatically, and as soon as it boots up, all the honeypots are configured, the network Suricata is configured. There is no interaction required, and the system sends alerts right out of the box to the Telecom backend. So the hardware requirements are really low. The minimum requirement is 2 gigabytes of RAM, 40 gigabytes of disk space, while the recommended requirements are 4 gigabytes of RAM and 80 gigabytes of disk space. So let me tell you a little bit on how the whole solution works. On GitHub, we create Docker files. The Docker files is basically a blueprint on everything that Docker needs to create in a container, like the operating system, the source code, dependencies, everything that you need to create the image that you want to run on Docker. So this Docker file gets a commit into GitHub, and GitHub is connected to Docker Hub, and in the same moment as we do the commit into the GitHub, image will be built on Docker Hub. So this is really cool, because whenever we change anything in the Docker file, anything on the files that we have on GitHub, an image build will be triggered and submitted and deployed to Docker Hub, and within the matter of 24 hours downloaded onto Teapot. So your installation is always up to date. So we do this actually for all the 7 images and containers that we use on the system. So once the installation is finished, you have 7 images downloaded onto your client, and Docker then creates containers out of each of these images, and these containers are then run separately without any interference to each other. That allows us to run, of course, all the honeypots like Dionea, Honeytrap, Kippo, and Glasstop, all in parallel. So we have here the EWS container. This contains a log correlator and event transmitter that sends events back to HP feeds. On the one hand, so you can opt in into HP feeds. The default is the Telecom security dashboard, and you can also opt out of everything, and then you have the ELK stack and show all the logs locally within a beautiful Cabana dashboard. So all these containers are volatile, so we had to look for a persistent storage, which is running on the machine, on the host, and contains the configurations for the log correlator and the database for the Elastic search. All of these containers will be destroyed every 24 hours. So every 24 hours, we start the containers freshly from the images. And of course, we're looking if any new images are available, and these will be then downloaded onto the client. This has the advantage that every 24 hours, even if one of these containers gets compromised or something like that, we have a fresh installation, and it runs like fresh out of the box. So this is the dashboard that looks pretty much the same like the one that André showed you, except for one difference. Here you can select the community node, so that all the events you can see here are aggregated from community honeypots, which deliver information back into the community dashboard at the Sicherheitstower at Deutsche Telekom. So we now would like you to join the community, install your own Teapot installations, give back to the community. You can also provide new code if you want to, if you like to. On this site you can find not only installation information, but also an installation video. It's time-lapsed, so it shows you an installation of Teapot in 30 minutes, time-lapsed into 8 minutes. So thank you very much for your time.